I've got 45 minutes, right?
I gave you something.
Okay, I'm going to speak to you quickly and briefly about the LROC experiment and the data that we have on the ground, and encourage you to go see some of the fantastic presentations that are given in both posters and talks later on in the week that feature LROC data. This opening image is the central peak of Copernicus crater taken looking from west to east about noon. Let's see now. I'm not as clever as Rich. Plus or minus 1 degree, right? There we go. And now this is the same spot on the moon, but it's looking from east to west at sunrise. And the arrow is showing you, I'll back up, so you can fix on the same peak right there. And then here's a third view blown up at full resolution of the central peak looking from now again back to west to east at sunset. The problem we have with showing LROC images in presentations like this is a single LROC image is 5,000 pixels wide and 52,000 lines long. And they come in pairs, so you really get 10,000 by 50,000. So how do you put that on a PowerPoint? Well, you either grossly subsample or you cut out a tiny little postage stamp. This is a tiny little example of a tiny little postage stamp. Okay, the status, well, the instrument is nominal, and as Maria joked earlier, that's NASA speak for everything is fantastic. We get over 400 gigabits of image data per day. I think it's actually because the Mach has been so exceptionally good with managing data that we're actually getting about 450 gigabits of data per day, so they really get an award for that. We have over 500,000 Knack images on the ground right now with illuminated moon. I think there's about 700,000 Knacks, period, but a lot of those are small calibration images taken at night on the dark side of looking out in space. So that translates into 1.4 times 10 to the 14 reflectance measurements. I don't even know how to say that, and it's such a big number. So over time, it's our goal to map the whole moon with the Knacks, with spatial resolutions ranging from 50 centimeters to 200 centimeters per pixel. The WAC, there's about 145,000 images on the ground. But really, the bottom line is that we've mapped the moon 33 times, nearly completely, and every single map has got a different photometric geometry, so it's not a redundant data set. We were in that 50-kilometer orbit for 2.17 years, which resulted in a fantastic data set that's on the ground, and all of that's in the PDS. As Rich mentions, there were 2 months where we were at a low periops, and here's an example right here of the Apollo 11 landing site taken from 25 kilometers above, actually I think it's 22 kilometers above the surface. You can see the footpads of the LM right there, it's, just like you were there. The new orbit brings up new opportunities, and Rich gave you a good introduction into that. If I can get this, there we go. This is a question that people are always asking me, well, how much coverage do we have? And it seems like a simple question, but it's not. So at the poles with the narrow-angle camera, of course, we've imaged everything that's illuminated several times. Then when you get down to the equator, it's about 35%. But then I ask them, well, do you want a noontime image or do you want a sunrise or sunset image? Because they have very different scientific uses. One's good for albedo, the other's good for morphology. So the first column there are noontime images with beta angles 0 to 45. So you can just say that we've covered about 30% of the equatorial region at noon. And then at sunset or sunrise, about 37%. Those images don't always overlap, so they cover more total territory. So it's about 55% if you just want to say there's an illuminated pixel in that area with the Knacks. And again, the goal is really to image the whole moon. And I'd really like to get high sun and low sun for the whole moon. I think the scientific community would also. Okay, there's a lot of work that goes on behind the scenes that allows scientists to do what they do. And one of these is getting this absolute calibration of the geometry of the images down. And it's an iterative process. The Lowell team works really hard, and they do crossover analysis of their tracks. And they improve the spacecraft ephemeris, which are the SPK kernels. And every time they give us improved kernels, we get much closer. This is just an example of what we do. There's the Apollo 11 descent stage still sitting on the surface. We've imaged the Apollo 11, I don't know, something like 20 times. The red dots are where we think the descent stage is just from the spice without any final corrections. And the blue are final corrections. And you can see that circle's getting smaller and smaller right now. So we originally improved the cross-track accuracy to 70 meters plus or minus 25 meters. And the down-track accuracy is 25 meters plus or minus 15 meters. We recently found out that there's a light time correction that wasn't being correctly implemented. And so these plots are already out of date, and they're only going to shrink. So just think of it as this amazing ability when you reproject a Knack image on the frame, and you want to know the location of a boulder because you're planning a traverse for a rover or a future astronaut, you're going to know where that is. I'm going to guess eventually within 20 meters. It's totally amazing. Okay, and then the left to right offset, some of you may have noticed if you're using ISIS and reprojecting the images that where the pairs overlap, they don't completely come together as you might had hoped and expected. Oh, I've got to watch one more time here because I usually end up going too slow. Okay, this is just showing you now when you project a left and a right that they come together within about a half of a pixel. So that's our relative pointing. Here, this repeat coverage is incredibly useful for photometric reasons because we get an image taken over, a bunch of images taken over a range of photometry. This is supposed to be a movie that's supposed to be playing now. And they assured me it would play automatically. Is there any magic that anybody can do back there? Okay, well, magic, yeah, here we go, perfect. So what you're seeing is Apollo 12 landing site from sunrise to sunset. And you see the light move around. And if you look very closely and you can watch it repeatedly, you can actually see the shadow of the flag marching around the flagpole. If anybody wants to see this, just come by and I have on my laptop. There you go. How cool is that? Okay, and again, cartography is incredibly important to me and about 20 other people. A lot of scientists don't really care about it, but it is important. Okay, the fixed orbit is really a misnomer because it's not. It's just really a low energy orbit. But typically the altitudes, it's 35 kilometers at the South Pole, but it really ranges from 30 to 50. And it's 60 kilometers at 45 south, 110 kilometers at the equator, 165 kilometers at 45 north, 190 kilometers at the North Pole. And just to give you a flavor, it really ranges from about 180 to 215 at the North Pole. If you want to translate that into what's the resolution of the Knack at that particular latitude, you just put a decimal place right there and you convert it from kilometers to centimeters. So at the equator, we're getting about 1.1 meter per pixel right now instead of the 50 centimeters that we had during the nominal mission, but still, it's a totally amazing image. Okay, and this just shows that the new opportunities we get since we're up higher. Now we can get these contiguous mosaics of features of high interest by just slewing over. Say that you have 5 orbits. The first one you slew over 10 degrees, the next one 6 degrees, the next one you're looking straight down. Then you slew 6 degrees in the next orbit, and then 10 degrees in that orbit. You can build up these mosaics like this of Giordano Bruno crater right here. That's actually 8 Knack images. Okay, this is, and also we get, since we're up higher, now we can see broader regions, and this is most of you will recognize this as the Taurus Littoral region. When we used to be able to go to the moon, we landed right there. Astronauts traversed over here. There's Shorty Crater, and then back up here and over. So it gives it a sense of scale. Here's a very famous picture that was taken during the Apollo era. It's very similar to this oblique that we took right here, except you'll notice that that's actually the command module below the lunar module, which is pretty amazing. You can see in the Knack image, the command module is now gone. Okay, this is just to give you an idea. Again, remember, we always have to decimate these beautiful images to put them on the screen. This is a full resolution blow up out of the LROC image, and there's Shorty Crater. That's where Jack sampled that orange glass right there, and here's Lee Lincoln Scarp. They drove the rover right over this and right in there. It's pretty amazing. Okay, this is a recent oblique image of Aristarchus crater, the south rim. In fact, this just came down a few days ago. It's 40 kilometers in diameter. I'm going to zoom in on the central peak here to show you some of the amazing data that we actually can collect with this instrument. There's the central peak. It's about, I think, 7 or 8 kilometers across right here. This is a brightness profile down here. So there's the beginning and there's the end. You can't read this scale, but that's 0.1. This is I over F, and that's 0.35. So if you look over here, this is that central peak where that profile goes across. So if you use this material as the baseline, the really bright streak in the middle is 3.5 times the reflectance of that standard right there. And then this middle gray unit over here is 2 times as bright. The Knack has an incredible dynamic range, so we do not saturate, and you can work on the photometry with these data sets. And the bottom line here is MSQ, Mail and Space Science Systems, builds fantastic instruments. Need to toot their horn as much as possible. It's really, really a fantastic instrument. Okay, this is, again, I showed you the Giordano Bruno featured mosaic, which we can get from the higher altitudes. I'm just going to skip to, maybe I'm going to skip to, now this is a movie that will play, because someone will magically do something. There we go. And this was where I took that, well, I didn't do it. In fact, I didn't really do anything, but talented people who worked for me took a mosaic of digital elevation models that we made from stereo pairs. I don't know how many there were. There was maybe 6 or 8 stereo pairs, made a digital elevation model, and then draped this mosaic over it. Now we can fly around inside Giordano Bruno crater. The walls of this crater, there's no vertical exaggeration here. The walls of this crater are above the angle of repose. They're 40 to 50 degrees in the upper half. It's totally amazing. Look at this. And if you go and get the nadir images, look straight down on here, you can spend weeks and months looking at the details preserved in the bottom of this crater. I'll just be quiet for a moment here. There's all sorts of fantastic impact melt deposits. Look at, you can see the little swirl where the impact melt float around. I don't know what these dark deposits are up on the rim. Come back around. And the Knack stereo data is totally awesome. We're making 2 meter per pixel digital elevation models for key science targets. Okay, here's I can't help but show off these great pictures. This is another image of Giordano Bruno that was taken. Here's the limb, the lunar horizon in the background. Can't even see down into the bottom of the crater because we're down too low and it's a 79-degree emission angle. Can't tell you how important these repeat observations are to follow up on discoveries that were made not only with LRO data, but with Selene and other spacecraft that are in orbit around the moon right now. This is the same pit that was discovered by Kaguya, which is probably a skylight taken under different lighting conditions. That rock right there is this rock right here. We tilted the spacecraft over when the sun was just right because we wanted to test the hypothesis that this was an open lava tube. And sure enough, we could see underneath an overhang. Everything you're seeing to the right of that arrowhead is underground. Okay, and then we've been imaging impact melt deposits under different lighting conditions. Actually, there's an automated program that goes and finds these pits from high sun images. So far, we've discovered 160 clot pits in 25 craters, and of course, it's an ongoing effort. The bottom line is that there's complex plumbing systems that develop in these large impact melt puddles, which, at least to me, is a surprise. Actually, I think pointing right up at the ceiling over there is the best place. Every month, we take a new mosaic of the North Pole and the South Pole, and as we build up this coverage, we are developing different strategies to get the best mosaics for your particular purpose. As you can see right here, this is the same area near the pole, but it's a very different illumination geometry. So if you just go and put random geometries together, you end up with not as good as mosaic as you do if you harvest data that have very similar azimuth and incidence angles over time that we're collecting. So we're filling in and making these fantastic mosaics from about 80 degrees up to the poles, both the north and south. The coverage at the south is a little bit more challenging now because we're down lower. Okay. No, that's no longer an optimal spot. Okay, we're imaging inside young craters in the mare and counting the number of layers that we see and then doing the geometry. And it's very common that these striations, which we're interpreting as actual flows or flow lobes, are on the order of 10 meters. This is just about everywhere on the moon, so now we're getting a handle on eruption conditions on the moon. Impact melt is one of my favorites. There's several. Whoop, that's telling me I'm running out of time here soon. Julie Stopar is going to give a talk on Wednesday morning where we've been cataloging and looking at many impact melt deposits. She's looking at smaller size craters. Jeff Plush has been looking at impact melts in medium to larger size craters. Stephen Kober has a poster, I guess it's up right now. So impact melts are really fantastic, so go check out that talk and these posters. Landing site photometry. Clegg et al. Has a talk showing that this mystery of the bright halos around all the landing sites, not only human, but the surveyor and the Lunar missions. We now got the data, so I think we're going to come to conclusion exactly what's going on. Okay, Knack Photometry. This is where we decimated all the Knack images down into a few pixels, looked at the change in brightness as a function of incidence, emission, and phase angle, made this photometry or albedo map of the whole moon from the decimated Knack data sets, and that gives us a function so that we can photometrically correct the Knacks when we're making mosaics. There's going to be some more talk about getting inputs for targeting, especially for stereo in the South Pole Lake and Basin. So go to the, what are these breakout groups? Is that what they're called? There's focus groups on Wednesday for SPA. And then Brad's going to talk about this in the talk also, I believe. Okay, I told you we've got 30 some odd complete global mosaics. So in color, stack them all up, and then you can drive happy parameter maps. And there's a very spiffy poster by Sato et al. That shows the first resolved Hapke photometric parameter maps for a body in the solar system. It's great stuff. Yep, just about there. Okay, 1 minute, and we got a 1 minute movie to end this with. Okay, if we could start the movie. And we're going to traverse from the highest point on the moon to the lowest point on the moon in the LROC wide-angle camera stereo digital terrain model. And we're headed east from the northern edge of South Pole Aitken Basin. There's Hertzsprung. Here's the Oriental Basin. This data set is out on the LROC webpage, by the way. Now we're coming into Southwest Oceanus Procellarum. There's Mare Humorum. Just look at the beautiful detail on this data set. There's Mare Nubium. We're headed down towards the equator. Apollo 16 landing site's probably up there somewhere. We're crossing the central meridian on the near side. I believe that's Janssen crater right there. We just crossed over the ever interesting Mare Austral, which I can never really figure out what's going on there. I believe this is Planck right here crater. We're back in the South Pole Aitken Basin. You can tell because the altitudes or elevations are getting very low. Here's Antoniadi crater. That little crater right there is where the lowest spot on the moon is, almost 10 kilometers below the mean radius. Okay, I don't have a conclusion slide, but I do have a conclusion. And the conclusion is that the moon is one of the most scientifically engaging and intriguing bodies in the solar system. We've got a lot to do. Thank you.
Okay, we're ready for questions here. That was fantastic. Who's got a question? We have a microphone. Ah, there's one. Mark, can you see?
Next question.
Do we have any other questions? Okay, I think they're just down. Here's one. Okay. Hang on a second. Could you say that again?
Is the photometry map data set available?
Yeah, that's, as you understand, that's a big job, and you should go talk to Hilo. I keep pushing them to get this project done, and it's my fondest desire that we would get that data set out sometime. I mean, I know he's making really great progress on it in the next 3 or 4 months to get it submitted to a journal.
Any others? Okay, thank you, Mark. Okay, great. All right. Our next speaker is David Page, and we're going to hear about